In this video, we are going to be examining Inconel 600 tubing over a wide range of frequencies so you can see the bad effects of using too low of a frequency to find flaws. And then we're going to watch how the phase spread changes up through 1 standard depth of penetration, 2 standard depths of penetration, and beyond. And after watching this video, you will know a lot more about phase spread and standard depths of penetration. Let's begin. So I started off by using a config with 10 kilohertz, 20 kilohertz, 40 kilohertz, and 80 kilohertz. And what you're looking at on the screen right now is 10 kilohertz. That huge signal you see on the Zetec screen is the tube support plate ring on the calibration standard. So that's on the outside of the tube, so an ultra low frequency, we'll see it pretty well. In this case, 10 kilohertz sees it extremely well. But what it doesn't see well at 10 kilohertz is the flat bottom holes. The calibration standard has a 100% through-wall hole, 0.052 inches or 52 mils in diameter. And then there's a 60% flat bottom hole from the OD, and then there's 4 20% flat bottom holes spaced around the circumference, separated by 90 degrees on the OD. But at 10 kilohertz, you can't see any of those flaws. So we're going to say that's too low. Next, we will go to 20 kilohertz. So here, I'm going to change my span a little bit. I'm maxed out on my span, but if you really look in at the center of that TSP signal, there's probably, maybe there's the origins of the flaw signals. But 20 kilohertz is still way too low to find flaws in this particular tubing. Okay, now let's go to my little hula buttons acting a little funky this morning. Come on now, there you go. Looks like I might need some adjustment to my hula button. All right. So there we have 40 kilohertz. What's that going to... Whoa! 40 kilohertz is starting to get into the zone where we can see the flaws. I should have used my other MIZ-27 for this. The button works better. All right. So at 40 kilohertz, you can clearly start to see the indications from the flat bottom holes. I'm going to change my span a little bit here. Right there. That's the one I want to change. So there's the TSP signal, the huge one. And there you got the 100, 60, and 20, but there's probably only about 15 degrees phase spread between the 100% hole and the 20% flat bottom holes. So can you imagine if you tried to do a phase versus depth calibration curve for this? You know what? Just for the heck of it, let's try it. So what we need to do a calibration curve, first we'd like to set it to set the 100 to 40 degrees, which is probably going to be something like that. Then I want to go over and put channel 5 up here, vertical. And what I'm looking at is make sure my flaws are going down and to the right first, which they are. And then what I would need to do is make my window size a little bit smaller so I can zone in on the 100%er. And then I would like to make my strip chart a little bigger like that. Okay, so now I'm going to go down to the 100. Make my window smaller. Up to my 100 right there. Gotta make my window a little smaller yet. So that's going to be our, is that our 100% hole? Let's see. To the other end. No, there we go. There's our 100. So let's go and put max rate on that guy. That's 32 degrees. So what I want to do is bring that guy. Okay, we're going to say that's about 40 degrees. All right, so let's go into the cal curve. We got 100% at 40 degrees. That looks good. But now we're going to go to the 60, which is right there. Measure that. Max rate. That's 50 degrees. And you're going to see that this is going to create a horrible cal curve that you would never want to use to size flaws ever. And there's our 60 right there. So we do max rate. That's 60 degrees. All right, so there's your sizing curve for on 40 kilohertz, Inconel 600, and very little phase spread there. So to size flaws based on phase, you'd be wildly inaccurate because every degree of phase that you change, let's see, so yeah, would be multiple percentage per degree, and just normal phase variability as you're moving through the tube, and you're getting subtle changes to fill factor when there's like tiny dents and ovalization of the tube and things like that. Just going to be off. So this is not a frequency that we would want to use for phase versus depth curves. All right, so now you've seen the phase spread for 10, 20, and 40 kilohertz. So now what we're going to do is go to 80 kilohertz. Now for 80 kilohertz, you're going to start to see a little bit better phase spread. Let me open my window up a little bit here. All right. And get my span a little bit up here. Yeah, now we're going to start to get a little bit of phase spread, but our amplitude is still quite low. Also, another frequency you would not want to use for phase versus depth sizing. Even at 80 kilohertz, that's probably, I would say let's see, it's not even 0.5 standard depths of penetration on the back side of the material. It's even less than that. So it's very penetrating. Okay, so now we're going to go to another config. So let's go to hardware config. And then, so we went 10, 20, 40, 80. Now we're going to start at 100 kilohertz. And then we're going to go to 180, which I believe is right at about, that's F90 frequency, so that should have about 90 degrees separation between shallow ID and shallow OD flaws. And then we're going to go to, let's take this to, we'll just double it. How's that? We'll go to 360, and then we'll go to 600. That should be a good one. And you're going to really start to see these phase angles take shape to be more in line with what you would see in a real life inspection. Oh, did I save it? I didn't even save it. Save config. There we go. Return. Now what we're going to have to do is reacquire the cal standard data. So I'm doing this in the dark, I'm going by feel. Okay, so I'm in the tube with the bobbin probe. I'm going to null the data, pushing the probe out the far end of the standard. Oh, I nulled it in the air. Can't do that. There's null the material. Push the probe out of the standard. Pull it back nice and steady. Okay. Now we're going to get to the good stuff. Okay, measure. All right, there we go. Wow, now we're really starting to get some good phase spread. So I have to go back to channel 1. Okay. I got to bring the span to a more manageable level. And then we know that the 100%, I'm going to make my window size smaller. We're going to do like this with a little hula button. All right, there's the 100. There's the 100 right there. So we need to take, is that the 100? You know how it is with eddy current. You got to take your good, sweet time. Make sure that you're on the right flaw. There's 100 right there. So we're going to take that. I'm going to rotate them around. Let's go here. Okay. Now just to make sure that that's rotated the right way. I'm looking at my strip chart here. That's going positive first, so that is an incorrect phase setting. Always got to be careful that you put differential starting down first. Okay, so now we've got 100 kilohertz set. Now I guess what we're going to do is step through the data and see what happens. So there's our 100% whole on 100 kilohertz. What? Did I have that backwards? That's the 100% whole, you idiot. Always good to have a cal standard drawing. And the reason I know I set that wrong is because my flaws rotated the wrong way. So now, no. There we go. So now when I scroll through the data, you got the 100, you got the 60, and you got the 20 right there. So if I open that window up a little bit, our phase spread now is getting to be like 60 degrees between the 100 and the 420, so better, but still not something that we want to use. So let's try 3, that's 180 kilohertz. So again, we have to set this one up. So I'll make my window size smaller. Go up to that's the 100 right there. Got to crank a little span into this so we can get it around the screen. Okay. And change my window size just a tad. All right, that's a little bit better. That's like, what, about 75 degrees phase spread between the three. Then we're going to go to channel 5. Wow, that one's getting a little bit more interesting. Okay, now without even setting the phase angle on this one, here at 360 kilohertz, we've got over 90 degrees separation just between the 100% whole and the 420s. So this is actually, we went beyond F90. This is getting more into prime frequency territory where your phase versus depth curves will be a lot more accurate. So to demonstrate that, let's go in here. So that's channel 5. I'm looking at my channel 5 strip chart to make sure I've got them rotated the right way, which I don't. Okay, now is that right? Let's see in a second. 100's going to be the first one there. This is really something doing this in the dark. Going by feel. Okay, so that's the first one is my 100 right there. So I have to change my rotation. Change my rotation. That's pretty close to 40. All right. That's just what I wanted. So I'm going to go here and hit max rate. It's 34 degrees. I need to change my rotation just a tad. We'll call it that. It's close enough for the purpose of this. Max rate, 38 degrees. No, you know what? We like to get things perfect here for this video. Even though it takes a few extra moments. Got to be patient with Eduardo. Okay, let's try that. Measure, max rate, 40 degrees, perfect. Analysis curves, 40 equals 100. That's already in there, so that's good. Next, we will go to the 60, which is right there. Max rate, that's 94 degrees. Cal curves, we're going to change that one to 94. Our curve looks all messed up, but trust me, it'll be fine in a minute. 94 degrees, and then there's the 420s. So we do max rates 136 degrees. And when we change this to 136 degrees, you're going to see the magic happen. And the curve looks absolutely gorgeous. What did I say, 136? So this has a lot of phase spread between the 100 and the 420s. ASME code says that phase separation needs to be between 50 and 120 degrees separation between the signal from the 100% whole to the 20% ODs. So this is an acceptable frequency for sizing with the phase versus depth curve. Okay, what's our next frequency to go look at? Let's see here, return. It's going to be 600 kilohertz. Well, I know when we actually do inspections on 600 Inconel 600 thermally treated, 600 kilohertz is too high. Now, why? Let's take a look at the data that will tell us. You're going to find this real interesting. What the heck? Can't even see any flaws here. Something is amiss. Window size, we're going to make the window size a little bit bigger. We need to scroll down there. We need to zoom that up a little bit. And I can see the flaws on my channel 5 strip chart. And 6. Now 7 vertical. Whoa. Oh, that's why. I need to go to channel 7. Okay, a little bit better. Now, 600 kilohertz. What we're looking at here, okay. That's the signal from the one at 40 degrees there. Hold on one moment, please. Don't get impatient with me. I'm going to change the span of our Okay, all right. Patience is a virtue. That's what your mother taught you, hopefully. So I got to turn that baby upside down. There we go. No, that's not right either, because I was on the 20%er. So that's going to be oh, I feel like the absent-minded professor this morning. At least I'm seeing what I'm doing wrong. I had the 100%er. First I was on the wrong signal, then I got on the 100%er and I had it rotated incorrectly. So that's the 100, that's 60, and that last one you see there is the 20. Now this is a crucial point that I wanted to make with this whole video, and that is when you're choosing what frequencies to use for a bobbin coil test, you want to target one standard depth of penetration to cover the entire wall thickness of your tube. When you do that, you're going to arrive at your F90 frequency, which in this case was somewhere around 200 kilohertz. At that frequency, your 20% flat bottom holes, came in substantially less than 180 degrees. When you target 1.6 standard depths of penetration at your full thickness, that's going to land a shallow OD flaw really close to 180 degrees. And if you've never thought about it before, I mean, the way you've been taught, either in school or in a training course, is that the flaw plane is between 0 and 180 degrees when you're doing eddy current testing for surface, right? And that is true. But the reason that you get the flaw plane to be from 0 to 180 degrees is from operating from the surface to 1.5 or 1.6 standard depths of penetration, during your test. Using those standard depths of penetration will give you between 0 and 180 degree signals. But once you start to increase your test frequency such that the far surface of your material goes beyond 1.5 or 1.6 standard depths of penetration, then you're going to get what we see here, and it's not a good thing. So there's our 100% hole. There's our 60% hole. But look what happens to the 420s. The 420s are now at 185 degrees, so outside of the flaw plane. So at 600 kilohertz, you could easily mistake a 20% hole, flat bottom hole on the OD to be probe motion if you just looked at that frequency, right? Now, if you rotated down through the frequencies, you would see that signal clearly rotate counterclockwise with decreasing frequency. But right here, we know it's just too high of a frequency. So we need to crank the frequency back to about 500 kilohertz to bring the 420s, back into the flaw plane, what's considered the flaw plane. So now we're going to go to the next phase of this experiment. And since 600 kilohertz has already puts the 420s beyond what's normally considered the flaw plane, we'll just start at 700 and go up from there. So let's go 700, and then we'll go to 800. And maybe this is the last time I'll have to change my config because you'll get the drift after this one. 900 kilohertz. And then we're going to go to 1 megahertz. Got to know your math for eddy current testing, at least somewhat, at least some math. 1 megahertz. That's very, very high for this particular test. It's not going to work, but it will work for this demonstration. Save config. Return. Got to require the data again, right? So insert the probe into the cal standard. I'm going to null the instrument. There we go. Pull the probe through the cal standard. Okay, stop acquire. Okay, I gotta zoom the data there. Measure. I hope you find my commentary mildly entertaining. Okay, so I'm nulling the data. Okay. Let's go put something else up in the strip chart there. That's channel 1 vertical. Okay. Get the span to a manageable level there. Then we're going to go to well. well. Okay, there we go. That's more in line with what I was needing. So 700 kHz, see the flaws, nice. That's the wrong way, so, okay, hold on. This is where it gets a little tricky because my frequency is too high. So that's going to be my 100 right there. I think we'll know once we get it rotated around here a bit. Yeah, I think that's the 100. Okay, look where the 60 is. That's normally where your 20% flat bottom holes would be. But because our frequency is so high, instead of being like at 90 degrees, it puts the 60s over there at about 150, 160 degrees. But when we go to the 420s, look where they're at. Now they're down to 100, or no, they're down at 14 degrees. What's wrong with this signal here? Ha! You're such a moron this morning, Eduardo. I tell you, it's easy to get messed up when you're looking at squiggly lines this early in the morning without enough coffee. Measure. Time to make the donuts and get the coffee. Okay, let's see if we can do this a little bit better here. Maybe I was in a rush, and we know that rushing is not something good to do when you're eddy current testing, because you are looking for critical flaws to ensure the safety of the public on a daily basis. Now, finally, I got it right. There's my 100% hole, but it's upside down. Tell you, when you're running too high frequencies, it's easy to get off a little bit. One vertical, it shows it going. It shows it going down and to the right. Oh, got it. If you look at the signal on my left-hand strip chart of the 100, you can see it goes down, to the left. That's down first, then back to the right. But what I was looking at was the signal from the 420s, and that's going up first. Well, that's what it does when you're using too high of a frequency. So there's 100, there's a 60, and the 20s actually, what would normally be the down part, since it's so far over, it actually goes up first, and this one measures at 210 degrees. So this is already way, way, way too high. And the signal's getting smaller because at a high frequency like 700 kilohertz, you got the skin effect, and your eddy currents just don't punch as deep in your signal. There's less eddy current density at this depth with such a high frequency. Your phase is increasing because it takes longer to get down to the 420s. And then because your eddy current density is getting weaker, your response is going to be less. Also, the center frequency, or the optimum frequency for this particular coil in this particular bobbin probe, it's probably centered at something much lower than 700 kilohertz. So it's really just not that sensitive at 700 kilohertz. Okay, so you can already see the dramatic effect that using too high of a frequency can have. But now we got to take it to the next level, which is 800 kilohertz. So that's going to be channel 3. Put that on my strip chart. And then we're going to have to go to measure. Measure. I'll do something to my span here. Okay, wow. Measure. My 100's going to be the first guy right there. Oh, this is great. I have to make my window a little bit smaller here so we can see what we got going on. Now, I believe that that is by 100%er. And it is, because if you look at my strip chart here on the left, that little guy right there, is going to be the 100. So I'm going to take my span. There we go. So yeah, the 100%er, we've got it rotated down and to the right, which is where it needs to be. And we're going to measure it just for the heck of it, see where we're at, 46 degrees. We can crank that down a little bit because I know how much you want Eduardo to be perfect. Measure max rate, 42 degrees. 42 degrees. Boop, 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 boop. That's probably close enough right there. Max rate, 40 degrees. All right. Now, when we go to the 60s, the 60s are at about 160 degrees. The 420s go down even further now. They're measuring 217. Now, we will go to our next phase in our experiment, 900 kilohertz. Okay, then there's 100. Crank down the volume, let's get them on the screen. Put that baby about 40 degrees, which is right there. Now our 420s are let's see here, max rate 52 degrees. So we're scrolling up through the data. Let's see, 3. Oh, I'm looking at the wrong thing in my strip chart. See, attention to details are important with eddy current testing. Null. So I had my 100%er set upside down. Now we crank the 100 back around. That's the correct phase setting. We'll assume that's 40. And the 60s now come in at about 170 degrees, 160, something like that. So there's our 420. So what's that read? 231 degrees. So this would be probably 2.3 or 2.4 standard depths of penetration, equaling your part thickness. Way, way, way too high of a test frequency. You'd get a really good phase spread. Do you want to see what the phase spread would look like on this, just for the heck of it? Yeah. I mean, I'm even curious. So we'll go in here and we'll hit max rate, 40 degrees. Analysis curve. 40's at 100, that's good. Now we're going to go to the 60s. We're going to max rate it. That's 154 degrees. So I'm going to change that number to 154. Don't worry about the curve shape. It's going to be wonderful in just a moment. And then now when we go to the 420s, wow, that's crazy phase. Max rate, 231 degrees. And again, when I correct these numbers, it's going to correct the curve. Ah ha ha. Notice how Zetec does not even let me go beyond 178 degrees for the curve. Maybe that was Clyde Denton's way of saying, hey, don't go there. This is too high of a frequency. But if he didn't, if he wanted us to play around a little bit, he would have took the locks off of 0.4 here and let us go as high as we wanted. But it doesn't make any sense to go beyond 180 degrees because the test frequency you're using is going to be too high. Your amplitude of your shallow flaws is going to be too low. It's going to make analysis confusing because you're going to be operating outside of the normally considered flaw plane 0 to 180. Okay, so our experiment's not over yet because we still have this frequency to look at, which is 1 megahertz. And we might stop it after this because I think you get the drift by now. Look up here and all my data again. The first one's going to be the 100. That's 100 right there. And we're going to span that or change the phase to be right there. Make sure I'm looking at channel 7 vertical. Okay, so I got my 100% upside down. Okay, it looks good. Now, there's our 60. There's a 20. That's an interesting phase, isn't it? Okay, that's as hot as I can make my span right here. And I have a drive voltage of 16 volts in my, that's throwing a lot of voltage at my coil. So this is starting to get into the zone where we're not going to be able to see the 20 anymore. But what is our what is our phase angle anyway? Let's check it out. Max rate. Now we're at 257 degrees. We're actually starting to get pretty close to, that's like 2.5 standard depths of penetration, whatever. And yeah, we're going to have to crank this a little bit more because now I want to see where 3 standard depths is. And if we can still see the 420s. So let's go to 1.2 megahertz. What? Uh-oh. The MIZ-27 only goes to 1 megahertz. So you know what that means? This demonstration is over. But if we went to higher than 1 megahertz, you would see that 420s, they would get smaller still, and they would keep on rotating around. And then once you get to about 345 degrees or so, that's roughly where 3 standard depths of penetration occurs. And you just don't want to be there in eddy current testing. If you look at the logo on my YouTube channel, you'll see what I call the eddy current tornado. And it's got the green eddy currents on the first layer. That's your 1 standard depth of penetration layer of eddy currents. That means they're robust throughout the whole thickness of your test material. The middle section of the eddy current tornado is yellow. That's by design. That's leading up to the point of about 1.6 standard depths of penetration. And then when you get into the red, that's when you're getting beyond where you want to be. Eddy current density is getting way too low, and the phase angle of your signals is getting way too high. So that's the perfect formula for missing flaws, and you don't want to do that. So be safe. Target 1 standard depth of penetration to equal the full thickness of your test material. That'll give you a good detection frequency. And then if you double that frequency, that should put you in the ballpark for what's called the prime frequency, and that will be a good frequency for using phase to depth curves for sizing the depth of flaws. And of course, always check your procedure and verify that your assumptions are correct by looking at the cal standard and seeing that the signals behave the way you expect them to. All right, enjoy the video. Please like and comment, subscribe, all that good stuff. Have a nice day.